Hi everyone, welcome back to another video. So in this video I'm going to be showing you how I take my lecture notes, which are, to be frank, rubbish, and convert them into notes that I can actually use, and how I actually learn from my lectures. So I've just started my two modules, first instrumentation and control, and secondly electrical and electronics principles 2. So in this video I'm going to be going over my lecture notes from electrical and electronics principles 2, which is basically like circuit analysis. That's what I did my first year, which was Thevenin's, Norton's theorem, superposition, nodal mesh, all the rest of that. So in this module, I'm going to be basically doing the same, but with AC. And yeah, to be honest, I don't really actually even know what I'm going to be doing too much because the lecture wasn't that great. All right, so the main thing that I'm going to be doing here is I have my lecture notes here, as you can see. And the notes are basically terrible. And the reason for that was, I'm sure you guys can relate. I listened to the lecture. I understood about 2% of it, and half the time I was falling asleep or just confused. So basically, if I was to just take these notes and try and just continue on with my work, which the lecturer has already assigned, I'd get absolutely nowhere. So as is the case with most of you guys, which is probably why you're even on the channel, you learn from YouTube and you learn from Google. So I'm doing the exact same thing as well. I'm basically going to be learning from YouTube and learning from Google. So what I basically need to do is I need to get on to so the main way that I look at my lectures is I just see the lectures as a way of me finding out what the lecturer is telling me that I need to learn. I don't learn anything from lectures. I mean, it must be below 5% whenever it comes to learning from lectures. You do get, the odd occasional lecturer who's amazing, but let's be honest, most lecturers, they're brilliant people in the sense that they know their subject very, very well. They're an absolute boss when it comes to their subject. But the entertainment side, the presentation side is usually terrible. So it doesn't matter how good you know your information. If you can't present it, no one can learn from you. So yeah, I basically now have the information that I need to learn for my first lecture, and then I need to try and find a way that I can actually digest it and learn it. So I'm going to basically go through my notes and start converting them into notes I can actually use. So this will be the first type of video that I've done on this, but I'm going to do this basically for all of my lectures. So you'll see a lot more of this. So if this is what you're into, subscribe and let's get into it. Alright, so this was an introduction. I don't need any of this. It's fine. Does I need to go over complex numbers? So let's add that to my to-do list basically. Okay, so this is my Notion. Alright, let's go not lectures. Revising principles ones. That can get archived now. Let's do archived. Move that into there. Okay. Let's read my reading list down to the bottom. Subjects, Google. Get rid of this. Okay, those two books I actually want to go through myself. Okay, my thoughts, capacitors, inductors, AC. So we can get rid of my thoughts now because I kind of know exactly what we need to learn. Alright, so let's do need to learn. And then we can do complex numbers. Okay, so I need to learn complex numbers, and then I've got to learn about it's like AC, but the whole thing is I actually want AC. That's fine. Okay, but let me just I'm just wondering if I should, I'm just going to quickly, because I can't remember really what complex numbers are. I remember it's like an I number, so let's just complex numbers. Can't really see my screen. Okay, so complex number is a number that can be expressed in the form of a plus bi. Yeah, I remember. The real part and the imaginary part. So I'm not going to go into complex numbers right now too much. I just want to have just an idea of it. Complex numbers, a plus bi. Alright, so what I like to do is I like to test myself. So I'm going to... there you go. How is a complex number? How is a complex number structured? And then put that into there. So what I'll do is I'll test myself on that probably tomorrow. I'll come back and I'll say, how is a complex number structured? And I just need to remember that it's a plus bi. A being the real part and bi being the imaginary part. So let's check if I'm right. Yeah, real part and imaginary part. Okay. So although my lecture yesterday, it wasn't on complex numbers, so it's not. Just adjust my camera. My lecture wasn't on complex numbers, so it's not that important, but still something that I need to learn. Just give me this cable anyway. Okay. I'm trying to get a better understanding of it. I know there's that like I squared is equal to minus 1, I is equal to the square root of 1. Okay, a complex number consists of a real part and imaginary part. I squared is equal to minus 1, I is equal to the square root of 1. Don't really get that. Notice that the pattern repeats every fourth power. I to the power of 0 is equal to 1, I to the power of 1 is equal to I to the power of I squared is equal to minus 1. Okay, I'm not going to get it like that. So real numbers are like 1, 12.38 minus, okay. Nearly any number you can think of is a real number. Imaginary numbers when squared give a negative result. Okay, there you go. So imaginary numbers when squared give... So again, like I said, my lecture wasn't on this. So, you know, I'm just spending, 5 minutes on this quickly. So imaginary numbers when squared give a negative result. So what question can I put? I can do what happens when you square an imaginary number? Okay, so I can test myself on both of these now. So how is a complex number structured? It is a plus bi, a being the real part, bi being the imaginary part. Correct. And what happens when you square an imaginary number? When you square an imaginary number, it gives a negative result. Yep, nice. Okay. Normally this doesn't happen because when we square a positive number, we get a positive result. 9 times 9, 81, yeah. When we square a negative number, we also get a positive result. Minus 2 times minus 2 is equal to plus 4. Yep. But just imagine such number exists because we want them. Okay. Let's talk a little bit more about imaginary numbers. The unit imaginary number, like 1, for real numbers, is I. What? The unit imaginary number, like 1. Okay. Yeah, got it. So what is a unit? What is the unit imaginary number? What is the unit for imaginary numbers? I find personally the only way that I learn is by doing this. If I just take notes, especially on a computer where I'm just copying and pasting, man, my retention is close to 0. But when I test myself like this, I learn a lot. All right, so the unit imaginary number, like 1 for real numbers, is I, which is the square root of minus 1. Okay, where did that come from? I is the square root of minus 1. Okay, I is equal to the square root of minus 1. Okay, so what numeric value is I? I think that's a good question to ask. Let's just check. There's no numerical value of it. It is not a real number. It is defined. Okay, so this is good thing I didn't write that question down because that would be incorrect. Incorrect question, that is. Usually the notation for I is not capitalized. Think of I as a direction, not a number. Numbers can be written on a plane, right? They have two dimensions or components, up and down, left and right. The up and down direction is the I direction. The up and down direction is the I direction. Okay. Yeah, of course. If you think about a plane, yeah, got it. Okay. The x-axis is going -1, minus infinity, 1 to infinity. The left and right direction is the other part of the number, which is the convention, which by convention is written first. 5 plus 3i. Okay, so I is defined by the relation I squared is equal to -1. Got it. Okay, so not what is the value? What is the value of I? That's probably a better question. And then I is defined by the relationship I squared is equal to -1. All right, so I'm going to leave that there. I've got 4 questions on complex numbers. I haven't actually started with complex numbers yet in my module, so that's why I'm not going too deep into this. There's a whole bunch of other stuff that I've done that I did yesterday morning, which I didn't understand, basically the whole thing. So I'm going to move on from that, and I'm going to come back and test myself on that daily. Let's move on. So network analysis, I've crossed this out because that's a serial number that they gave me. Okay, so he mentions that AC for voltage and current. AC voltage, although it's alternating current, it also applies to voltage. AC voltage is equal to alternating current voltage, which basically means AC just alternating voltage. So I'm okay with that. Here he mentions that this is a steady 2 amps. I'm also okay with that. This is not AC because it doesn't go below the 0. So I'm okay with that. So this part of the lecture I was fine with. Then he went to sawtooth, direct AC, square wave, and sine waves, and you just lost me there. So let's so what I do now is here on my notes, I'll add a page here, and then because the thing is, when you're taking notes, it's just all rapid, like you're just writing, and lectures going at 1,000,000 miles per hour, so the notes end up being rubbish. So I try and always correct my notes. So let's do I don't even know what would this be. Different types of waves: sine, square, triangle, sawtooth. Okay. Different wave signals. I don't even know if that's a correct terminology for it. Let's check. Different types of waves. Electricity. Yeah, this is kind of what I want. Right, this is basically waveforms. The form of the form or shape of f in formula involves the argument what? Okay, constant values, blah blah blah. Right, this is not no, okay, amplitude modulation, frequency modulation, phase modulation. The amplitude of a wave may be constant. Okay, this is not what I want. Okay. 5 main types of technology used, including absorbers, attenuators. Okay. Alright, if I just type in different types of waves, was it sawtooth, sine, what's the other one? Triangle, and square. There we go. The difference between waveforms and why it matters. Waveforms are the starting point of synthesis and of all sound. In a synthesizer, an oscillator creates a repeated signal of a waveform. This waveform is what gets altered through synthesis. Blah blah blah. Okay, sound. This is to do with sound, but if they just teach me about should I just look for something in terms of voltage? A sine wave sounds like it looks smooth and clean. Okay. I don't get that at all. Yeah, no idea. I don't know what's going on there. Let's do it in terms of so put in speech marks voltage. There you go. Okay, so oscillate tutorials. Technically speaking, okay, so these types of signals waveform can be used. What's funny is, you know, they haven't taught me anything like this, and the way they just jump straight into it in the module is painful, man. I didn't know. I knew there was different types of waves, but I don't know anything about them. So technically speaking, electrical waves are basically visual representations of the variation of a voltage or current over time. In plain English, visual representations. Okay, so wave is a, well, let's see, what's the electrical waveforms? Okay, let's call this different electrical waveforms. Electrical waveforms. Different electrical waveforms. Okay. So, you know, a waveform is a visual representation of a variation of a voltage or current over time. Okay. So visual. So let's put waveform, a visual representation of the variation of voltage or current over time. All right, so let's get this. So we've got lecture 1. Okay, this is what I need to, this is my to-do list, but I'm wondering if where should I put my questions, basically. Okay, so questions, and then wondering how to group it. Okay, let's do a page questions. This is what I like about Notion. You can basically design it however you want, which is nice. And then let's put lecture 1, and then like that, or maybe I should do lecture 1 like that, and then put them inside there like this. Yeah. Okay, so define a waveform, and then a visual representation of the variation of voltage and current or current over time. Okay, so I'm going to look away and just test myself. So define a waveform. A waveform is a visual representation of the variation of voltage or current over time. That variation part, that's important. Okay, I'm comfortable with that. Yeah, it'd just be really helpful if like people define stuff before they start teaching it to you. Okay, so there are many different types of electrical waveforms available, but generally they can all be broken down into 2 distinctive groups. Nice. I love when people categorize things. Please, we need more categorizations. Okay, so unidirectional waveforms and bidirectional waveforms. Okay, let's do this. So what are the 2 types of waveforms? Unidirectional and bidirectional. And actually, what's cool about Notion is that you can do this. And you can actually turn these in. Oops. Okay, let me try and do this. What am I doing? Okay, so put that into there. That's in there already. Okay. There we go. That's what I wanted to do. So you can actually have that. So what are the 2 types of waveforms? You've got unidirectional and bidirectional. You define a waveform. A waveform is a variation of the, no, sorry, it's not a variation. It's a visual representation of the variation of voltage or current over time. A visual representation of variation of voltage or current over time. There you go. What are the two types of waveforms? You've got unidirectional waveforms and bidirectional waveforms. Then now I can define them here. So what is this? What is it? Define it. Let's put define it. Not define it. Okay, let's just read what it is. These electrical waveforms are always positive or negative in nature. Always positive or negative in nature. Flowing in one forward direction only, as they do not cross the zero axis point. Common unidirectional waveforms include square wave timing signals, clock pulses, and trigger pulses. Unidirectional, so they go one way. Okay, they're either positive or negative, because obviously you could get -2 amps of current, but it's only flowing one way. Okay, and a common example is square waves, clock pulses, trigger pulses. I'm okay with that. I'm comfortable. Yeah, I know that. So define it. Okay, so unidirectional, define it. Usually, if you can define it in your own words, that's a lot better. It's way more likely that you memorize it. Unidirectional would be, so they flow in one direction. Positive, and can be positive or negative. They flow in one direction, can be positive or negative, but never cross the zero line. I'm not sure what that means. They never cross the zero axis point. I'd like to have a visual representation of what they mean. So they can be so they can be positive or negative, but they never cross the zero. Oh, okay. So it could be below it, zero, or above it, but it never goes across. Okay, so but never goes across the zero axis point. That makes more sense to me. Never goes across the zero axis point like this does. Got it. Never goes across the zero axis point. It stays either above or below. Okay, I'm comfortable with that. And then now we can put as well here, we can put what are some examples of unidirectional waves? Unidirectional. So you've got the clock pulses, you've got trigger pulses, and then the other one was like a square something. What was it? A square wave timing signals. I don't really know what that is. Is that just like clock pulses basically? A clock signal is a square wave with a fixed period. Square wave. I don't know what that is, so I'm just gonna go with what they mentioned: clock pulses and trigger pulses, because I know what those are. There you go. And so now again, I could test myself. So define a waveform. A waveform is a visual representation of the variation of voltage or current over time. And then what are the two types of waveforms? You've got unidirectional and bidirectional. And then unidirectional, define it. It is, oh dear, okay. Unidirectional is like a signal, a waveform. Okay, a waveform that never goes across the zero axis. It stays either positive or negative and travels in one direction. Flows in one direction and can be positive or negative, but never goes across the zero axis point. It stays either above or below. What are some examples? You've got the clock pulses and the trigger pulses. There you go. You see, this is how I learn best. I'm comfortable like this. Okay, so bidirectional. I assume bidirectional means that it can cross the zero axis, right? These electrical waveforms are also called alternating. So we can call them alternating because that's probably more relevant to AC. Bidirectional or alternating, as they alternate from positive a positive direction to a negative direction, constantly crossing a zero axis point. Okay, so below zero represents going backwards, right? Okay, I get it. So that's why you have waveforms that go like this. So even though it's going forward, okay, because this represents time. Got it. This x-axis represents time. So although they're going forward, this being 0, makes sense now. So you got 5 volts, and then you got 5 volts, and then you got 5 volts, and 5 volts, and 5 volts. Got it. Okay. So, all right. I'm quite comfortable with that. Let's just write it down. So they alternate from a positive direction to a negative direction, constantly crossing the zero axis point. Bidirectional waveforms go through periodic change in amplitude. They go through periodic change. Okay, amplitude being this and this, right? With the most common by far being the sine wave. Got it. Okay, so bidirectional waveforms, they alternate from a positive direction to a negative direction. So they're always going forward in time, obviously, not going backwards in time. So they're always going forwards in time, but they're going from a positive direction to a negative direction. Flows from a positive direction to a negative direction. I mean, that's not really correct. It's that they alternate, because that would imply that they just go from positive to negative once. They alternate constantly from a positive direction to a negative direction. Always or constantly crossing the zero axis. Okay, I fancy a picture of these, so let's go. Can I get a more simple one? Can I get a more simple one than that? Unidirectional waveform. Why is a good picture? Like, I thought that would be simple. Okay. Versus alternating. Okay, so let's go with that. This one will do. I want one with a background. Why are they all the clear images? Confusing. Oh, goodness sakes. Alright, well, okay. There's a better way to do this. Basically, I can just screenshot like this. There you go. I'd prefer to have one clearly where I could see the bottom to the below zero, so I can clearly understand in my head that is below zero. Unidirectional. Okay, so can I do, what if we just bigger pulses? Do you guys not have a picture of it on their website? No. Okay, that's it there. It doesn't clearly show it's below zero. Go on, forget it. Don't want to waste too much time. Sometimes I do this. I get sucked into, doing silly things like, dealing with pictures instead of just getting the content done. Okay, and then bidirectional is obviously the standard sine wave stuff. Okay. All right, so I'm comfortable with that. Where were we at now? Okay, so whether the waveform is unidirectional or bidirectional, periodic, non-periodic. Well, you haven't told us what non-periodic and periodic mean. Symmetrical, non-symmetrical. Okay. Yeah, I don't really understand what you mean in terms of symmetrical there. Simple or complex. I saw a picture of like simple, complex stuff over here. I think. What was it? You might have been on the last page. Let's go back. There you go. That seems like a good picture. Sine wave, complex wave, triangular wave, square wave. We'll just keep that for now. Although this one's quite clear as well. Okay, so all electrical waveforms include the following three common characteristics. Okay, so all waveforms, have three characteristics. Number one, period. Number two, frequency. Number three, amplitude. Okay. All right. So, what three characteristics do waveforms have? Let's see if I can remember from my head. I know one of them is amplitude, the other one's frequency, and the first is period. Nice. Okay, so period, frequency, and amplitude. So amplitude, I assume, is like it's the like 5 volts, 4 amps. Frequency is like 50 hertz, 60 hertz, and period, I don't know. Yeah, I know it's like time. They talk about time. I don't know what period is. Okay, so this is the length of time in seconds. Okay, so time in seconds. Okay, that the waveform takes to repeat itself from start to finish. Okay, so you have a waveform here to here, and then it starts again. So this whole thing here is the period. Right? Yeah. So time in seconds, for waveform to repeat. Okay. The time in seconds for the waveform to repeat. Time in seconds for the waveform to repeat itself. Can I get a picture of that? Does it have it there? No. Literally, like my lecturer was first time he was like, yeah, so obviously the frequency is 1 over the periodic time, so f is equal to 1 over t hertz. And I was like, yesterday I was like, huh? You what? And that was it. Just from there, it just continued like that. And yeah, there's none of this explanation. It's not like they give you topics that they say, oh, hey, by the way, for my module, you need to know this. So make sure you brush up on this. There's none of that. You just go into the lecture and hope for the best or sleep. Okay. So the value can also be called the periodic time. Okay, so let's put this here. So, aka periodic time. Just make some space here. So time in seconds for the waveform to repeat itself, also called, and then I'll put that in there. Periodic time. Done. What am I doing? Okay, so also called I'm not the greatest at Notion. I'm still kind of learning. Okay, so also called periodic time. Cool. The time in seconds for the waveform to repeat itself. So let's put. I feel like I saw a picture of this. Let's put waveform period. Sine wave explained. One full cycle or period. Second period. Nice. Okay, that's what that's what I was after. I would like a clear one so that when I'm revising, because you know when you're revising, you just want something clean and simple. Too much on the image or whatever. Again, like I said, I don't. Sometimes I spend way too long looking for the correct picture. Did they say that this is on this one here? Yeah, is there one full cycle or period? Okay, so I'm just gonna quickly help myself out here by just highlighting this bit. And actually, if I wanted to be really cheeky, I could get rid of some of the other stuff. Make it a bit more clearer for me. Okay, so there we go. Okay, so tell me, what are the what three characteristics do waveforms have? They have period, they have frequency, and they have amplitude. Right? Yep. And so what is the period? The period is the time that it takes for the waveform to repeat itself. And it's also called the I don't know, man. What is it called? The periodic something? Periodic time. Periodic time. So what I do as well is when I get it wrong, if I get it wrong on the first day, I'll mark it red. And if I get it wrong any other time after that, I'll also mark it red. But when I start to get it right, not on the first day, I don't usually do this, but usually on the second time, third time, fourth time, when I get it right, I'll mark it as like a red, and then I'll mark it as an amber, then as a yellow, like as an orange, then as a yellow, then as a green, and then if I solidly know it, and I've tested myself 4, 5, 6 times, over a month or whatever, then I'll mark it as blue, and I won't test myself on it again. So frequency. Let's move on to frequency. This is the number of times I've actually got my lecture in 9 minutes, so I need to just wrap up here. But at least now, I haven't actually covered anywhere near all of the jargon that they went through yesterday. Like, look at this. Like, I don't even know what any of that means. They talk about omega and stuff. Actually, I do want to touch on omega. Because he said the word omega 50 times yesterday, and I don't even know what it means. Omega, symbol, meaning. Omega, last letter of the Greek alphabet. But why is I get it, that's the omega signal, but he's calling this thing omega. I'll show you. Where is it? This is omega. So is it supposed to be that? No. The omega W signal meaning omega W symbol. Oh, it's the lowercase version of it. They don't teach us Greek alphabet in school, so I don't know why. You just at least elaborate on the fact that what it is. Like, bloody hell. Alright, anyways. So then we just write something about this, I suppose. So we've got different waveforms. So let me just add a page in here. So I'm gonna continue this. I've got the second lecture of this in 7 minutes time. So I'm gonna continue this later, but just want to touch on So meanings, or let's put omega. And so you've got this thing, which is the ohms. That's for ohms, right? That's the capital omega. And then this weird W thing that looks like something very rude is the lowercase omega. Okay, so what does it mean in terms of electricity? Omega W lowercase electricity meaning. Omega symbol physics application lowercase physics alphabet. He's actually got like the okay. Electricity meaning. So I get that's the ohm, but what's this other one? Electrical magnitude units and symbols. I search for it. It's not even there. Omega, inverted omega, minuscule omega. Okay, pulsation. Cheers, mate. Cheers. How would was I supposed to guess that out of the air? This weird minuscule now. I thought it was a lowercase, so now it's called minuscule omega, and it is pulsation. So this W is equal to pulsation. What's this column for? Unit. Okay, so it's the unit of 1/seconds. The unit of 1/seconds. Okay, and what's this last column? Basic calculation. Okay, so basic calculation, and it is so omega is equal to 2. What's that? Is that supposed to be a times, right? That dot. 2 times pi. Just right. Let's do the sign for pi. I can just put 2 pi, right? Or no? Okay. Let's not. Just keep it the same as. It says 2 times pi times the frequency. Not gonna fit. And the basic calculation is 2 times pi times the frequency. Okay, so omega is 2 times pi times frequency, and that equals somehow pulsation. Okay, so again, I'm not in my studies. I'm not there yet to really understand what that means. I'm still, I haven't even gone on to frequency yet. So I assume maybe they're going to talk about omega here. But yeah, shout out to this website, electronics-tutorials.ws. Man, these guys, they saved my life. If I do more of these videos and you watch them, you're going to see this channel pop up a lot. All right, so my lecture is due to start in 3 minutes, so I'm going to jump onto that and sit there, maybe learn, I don't know, 1 or 2 things over the next 2 hours, and then yeah, I'll come back and do this and probably learn 15 things a minute. So yeah, I'll see you guys in the next video. Thanks for watching, and hopefully in the next video I'll give you an update as to how this lecture went. Cool guys, peace.